So let me just skip maybe the outline just for the interest of time. And in general, what I'm going to talk about is throughout the conference, we have been hearing talks saying, of course, a lot about InGaN. And the main advantage of InGaN is that as you change the indium composition in that alloy, you can basically span the emission through it or from it throughout the whole visible light spectrum. But in fact, gallium nitride is being used not only for photonics and like more complicated structures over here, but actually the huge growing field is the electronics made with gallium nitride. So what actually we found out at the beginning was that it makes gallium nitride perfect material for a monolithic integration. And the basic idea of the concept that we had that has been published last year is that we can use the metal polar side of a crystal, gallium nitride crystal, for growing a traditional LED, typical LED. In this case, this is just a blue emitting LED, while the nitrogen polar side can be used for high electron mobility transistor, which is just typical over here. And of course, there have been some works to monolithically integrate structures like that together, but they have always been using the same side of a crystal. And then obviously the two main advantages that we have over here is, first of all, in both cases, the growth both on nitrogen polar and on gallium polar side relies on well-prepared, optimally polished surface. So that's one thing. Of course, also we are leveraging the fact that now we can use all available surface because now we have twice the area because we're using both sides here. But there's another extra point here, which is really important for gallium nitride, and I guess optics, people doing optics with gallium nitride forget about it pretty often, is that gallium nitride is polar. So working with nitrogen polar side of a crystal, which is not that common in the community, actually brings you in some of the advantages. And first would be that for nitrogen polar high electron mobility transistors, you can actually expect nice performance at high frequencies because I think that the pointer is not working really well, but nonetheless, because your two-electron mobility, your two-dimensional electron gas is pretty close to your gates, so that gives you some freedom, some extra performance in high frequencies. But also, it has been reported many times that actually indium incorporation on nitrogen polar side of a crystal is it's much better. Like what's shown over here, this is just an indium incorporation. That's interesting. Okay. Anyway, yeah. You expect more indium to incorporate at nitrogen polar side. So this can be used for long wavelength emitters. So now what we chose to work with is the epitaxial growth by MBE. I again think that most people in the field are working with MOVP. So the general concept of MBE is that it's a high vacuum growth technique. So you need to make sure that vacuum during growth it's at the level of, say, below 1e-4 torr, and this brings you to the roughly the growth temperatures that are accessible by MBE to 750 C, because at higher temperatures your crystal starts to decompose in vacuum. So, yeah, but throughout the years, as people have been working more and more with MBE, we come up with a way to grow pretty nice crystals at relatively low temperature, and the work around the whole low temperature growth is to use metal-rich conditions instead of nitrogen-rich conditions. Right. So what can be done with this? We weren't actually a group working with LEDs too much. We were more concentrating on lasers throughout the years. So this is one of the LIV characteristics of our lasers. They were operating pretty fine. Actually, throughout the years, we have been also working with many different wavelengths, spanning from like UVA region roughly to 500 nanometers. So these are, by the way, lasing spectra of lasers grown at our institute. And actually, throughout the years, for many different generations, we improved on quality of these structures pretty much. And lifetime of these devices right now is exceeding even, at least we have been measuring it only for 400 hours, but expected lifetimes are more than 100 hours. And actually, even a pointer that we have made with a wavelength around cyan wavelength here, this operates for more than 10 years now. We have been using it at many conferences. I guess the lifetime is better than the one that we have over here. nonetheless